Whenever you have a structure with areas and you choose to support one of the area sides, you'll get area side results or reactions. And I'd like to talk about them and show you how to interpret them. In this example, I have a plate mesh created from an area, and that area has one side that's fixed. So this entire boundary is fixed. The other three sides is free. The way I'm loading this is, for the dead load case, I have an area edge load applied at this far right edge of 200 kips, and we're stretching the plates basically. For the live load case, I'm actually loading the area with a pressure load, so I'm going to be bending this slab as though it were a cantilever, bending it off of the left edge. And then the final load case loads we're going to look at is the snow load case. And for the snow load case, I have an area side load on this right edge, and my load direction is in the plus Y direction. So I'm actually going to be bending this group of plates upward. So let's now look at the results and the area side results that come from them. Okay, let's start off with the dead load case. In the dead load case, I am stretching this thing from left to right. And when we look at the results filter, we want to make sure and turn on area sides for what we're showing. And we take a look here, we'll see these green lines showing the area sides. And if we look at the legend over here on the right, currently we're showing in-plane shear in pounds per foot. Now then, let's select this side that has the reaction that we want to look at, and then go to the Results tab and look what's displayed. For this side, we're seeing it has an in-plane axial value, an in-plane shear value, no flexural behavior. The average values for in-plane shear are 0. For in-plane axial, we have 1,667 pounds per foot. And then for reactions, we have 200 kips. In-plane shear is 0, moments are 0. Notice how this 200 kips matches our applied load of 200 kips. So what are we talking about when we talk about in-plane axial? We're talking about the loads that result from forces perpendicular to the side. So it would be like the support reactions along this right edge that go in the negative x direction. So that's the definition of in-plane axial. In-plane shear would be the forces that would line up parallel to the area side. Many times you'll use area sides and model a diaphragm in a structure, and this would be this typical diaphragm shear that would be transferred to a shear wall. So that's in-plane shear. Flexural moments and flexural shear and overturning involve bending, which we don't have in this case, so I'll wait for a moment and talk about those. Let's now switch to the live load case. Remember, for the live load case, we're applying a pressure load and bending this plate mesh to where it is bending in the negative Z direction. So now then, if we click on our support area side and look at it, for results, we have flexural moment values and flexural shear values. We have average values, and then we have resultants. And if we look at the resultant values down here, we're going to see we have a moment and we have a shear. Those are basically the resultant moment, and it would be about, looking in on the edge, the moment about the y-axis would be the flexural moment value for this edge. The flexural shear would be the shear value in the Z direction. Another comment I want to make about this detailed list. Notice it has a range. What we're doing is we're looking at sections along the length of the area side, and because the moment isn't constant, we're just giving you a range of how it's changing from one side to the next. Same for the shear. So the detailed value involves the ranges of values. We take and average them to get the average values, and then we take the total resultants to give you resultant values. Final thing let's look at the snow load case, and now we'll go back to looking at it from the top. Remember, for the snow load, we were applying an edge load along this right edge in the global Y direction, and we're bending this mesh of plates up. Now let's look at the area side results. For the area side results, We have axial and in-plane shear, no bending, no flexural. Our average value for in-plane axial is 0. Our average value for in-plane shear is 83.33 pounds per foot. And when we look at resultants, the in-plane shear resultant is 10 kips, and the overturning moment, now that's a new one. What is the overturning moment about? That represents the resultant of the axial forces. Now remember, axial would be forces in the x direction along this edge, and they're varying from negative to positive values. So we're basically getting a bending stress distribution in the x direction along this edge, and because they go from negative to positive, they're producing the typical bending moment you'd get from a linear varying type stress distribution. The overturning moment represents the sum of those axial stresses times their distance from the center line of the area.